Hi, my name is Aagat, and I will briefly present you about the vector embeddings for text and GPS data. Moving on, why do we even need vector embeddings and what are vector embeddings? Computer does not understand textual data, or let's say any discrete data kind of. It understands numbers in nature. So we need a representation of textual data, image data, or let's say geospatial data into numbers. That's why vector embeddings are needed. So we can see that we have a embedding model here, and there are three type kind of objects here: object one, two, three. And then we can, if we pass this to an embedding model, we get meaningful vector representations. That is, we can convert these objects into numbers using this embedding model. And one feature of this is that similar entities have similar vector representations. Most of the embeddings are used in NLP, geospatial analysis or recommendation systems, and even other different fields. So, why do we even need vector embeddings? And more specifically, how does one hot encoding differ from a word embedding? So one hot encoding basically tells that, let's say I had 10,000 words are in my vocabulary. Now I will assign every word, I will have a 10,000 size vector, and I will assign a value of 1 to a specific word, and the rest would be 0 for that word. So let's say that in the case of uh, king, I had these many numbers in the vocabulary. One was assigned to this position. Similarly goes for queen. Similarly man, and similarly goes for woman. But the problem with this approach is that it has an exponential time complexity as it grows in size. Because let's say I have a vocabulary where I have around 1 lakh words. So every now and then I need to assign one to it, and the computation complexity would be very high. So I needed also, let's say that two things that is means king and queen, or king or man should be similar in nature. So they should have similar vector representations, but as you can see that they are not similar in nature when it comes to one-hot encoding. That's why what we do is that we need some kind of embeddings that would contain a meaningful representation in a short manner, and should also be computationally inexpensive or efficient in nature. We have several popular frameworks for text embeddings. One is Word2Vec, another is Glove, and the third is BERT. Word2Vec learns word representations based on co-occurrence. Glove basically factorizes the word co-occurrence matrix, and BERT uses transformers for contextual embeddings. I will briefly explain them one by one in the future, in the next slides. So, Word2Vec. The way Word2Vec has been trained is based on two approaches. The first one is a continuous bag of words approach, and the second is a skip gram approach. Talking about the continuous bag of words approach, I have in this kind of scenario, let's say I have a sequence of words, a sentence basically, and one word is hidden. So what we do is in continuous bag of words is that we predict the word that is hidden. This enables to learn the contextual similarity of that word with respect to other words in the surrounding. So let's say I had WT minus 2, WT minus 1, and WT was missing. So I was predicting WT in the continuous bag of words approach. Skipgram is entirely the opposite to this in nature. In this, I have an input word, and I then predict the context words. This enables to learn what the current word is meaningful with respect to other words. So that's why skip-gram approach, through skip-gram approach, we can learn the contextual, the semantic representations of various vector of various words, and also their vector embeddings. Now, word2vec was a good approach ideally, but it was failing on uh, where I required a large amount of contextual context to be carried along. So we came up with another idea that was BERT. So BERT stands for bidirectional encoder representation from transformers. It leverages a transformer-based neural network to understand and generate human-like language, but employs only an encoder-only architecture. So when we even train while training BERT, there were two specific tasks for which the BERT was trained. The first was mass language model, and the second was next sentence prediction. So in mass language model, what we do is that let's say I have a sequence of words, which is a sentence. What we do is I mask certain words in them, and I predict those words in the output. That's how so that it can represent, it can understand the context among different words. And in case of next sentence prediction, what we do is that I have two sentences, sentence one and sentence two. It can then tell that whether a sentence two would be next sentence corresponding to a sentence one or not. So that is like a yes or no at the output layer. And we compute the probabilities and then compute the loss and train it. Similarly, for Mars language model, we compute the probabilities of different words over a vocabulary, and then we compute the loss. That let's say there was a specific word at that should have been present at the masked position, but and we see that over the vocabulary what our model predicted. It predicted, let's say, is at that position. So we computed the loss and then calculate and then train the model again. Now I'll briefly explain how does encoder machinery work. That is the crux of BERT. So what happens is that every word in a sentence is first assigned a token. What tokenization process does is that it assigns a unique number to it. Now what happens is that we have an embedding layer. What these tokens go through to an embedding layer. The embedding layer has certain weights. It provides a vector representation corresponding to every unique number. Let's say I had a number 102. It would provide a unique, let's say 200 size vector representation. Then say I had another token whose value was 103. So it would assign, let's say, another representation, vector representation. Now these are the embeddings. Now what happens is that positional encodings are added at this point. What this does is that it tells how words are present relative to each other in a sentence. Then comes the self-attention mechanism, which is the crux of this. Self-attention, what it does is attention basically tells us the contextual understanding. It it calculates the contextual understanding among different words. So how the first word relates with every other word in forward and backward direction. It gives a certain value to it. So that's how self-attention works. Then it passes to a feed-forward neural network and outputs the certain probabilities. Uh, Then how does basically attention work in BERT? So as I previously explained, it works on the self-attention mechanism. Each word attends to all others in the sequence. And then most important advantage of this is that it can capture long range dependencies, and it also enables efficient parallelization. Because what happens is that in multi-head attention, let's say I had 786 size of array. Now multi-head would break down into eight parts. Let's say now 786 by 8 would be different stacks that would be distributed. And then they would at the same time parallelize and get computed into the embedding layer, into the feed forward neural network that is present here. Now coming on to the geospatial data embeddings, the question arises that why do we even need geospatial data embeddings? So let's say I have a latitude and a longitude point. I need a vector representation of it. Why do I even need it? Is because let's say the point had let's say I have a point called 40 degree 40 comma 45 and another point called 46.46 47. Now if I pass this as raw numbers into the model, it won't capture distance similarity as well as semantic similarity. By distance similarity I mean that how much far they are with each other, and semantic similarity means that if these two points represent a particular city, so they should be close to each other in a vector space. Their embeddings should be close to each other. That's why we properly need a geospatial data embeddings pipeline. So, and these are mostly used for route optimization and mobility analysis. One of the famous algorithms for GPS embeddings is deep work algorithm. What it does is that it first creates a graph. The way it creates a graph is that it decides the nodes. It decides the nodes on which whose nodes I need to validate the embeddings. So let's say these are several lat longs. Then it calculates the distance and constructs a graph. So then it starts from a certain node. Let's say I start from third node, and then it randomly walks along the graph and generates a sequence. So I have the following sequence called 3, 2, 4, 5, and 9, let's say. So this is a sequence, and this would closely represent a word sequence also. That's why what it does is it then passes it to a skipgram model, which I told in the previous I explained in the previous section. That is called word to vec. It passes that into a skipgram model and then generates the embeddings for every word. And the way it works is that it the loss function which it uses tells forces it that two nodes which are close to each other in a vector space should also have closer cosine similarity among between them, and then that enables them to learn semantic similarity as well as the distance spatial similarity. So that is one of the popular algorithms for GPS embeddings. Now, certain applications of text and GPS embeddings, semantic analysis, search, and AI chatbots are several text. ChatGPT is also one of the most powerful engines that are running today, and also based on users text embeddings. GPS also for GPS purposes, we need route optimization, location-based recommendations. For these type of algorithms, we need a vector representation of GPS lat longs. And then we use those embeddings to learn special, let's say, observations or patterns in geographical data. Now, text embeddings capture space semantic similarities. GPS captures spatial as well as semantic. Both represent high dimensional data meaningfully. Now, challenges would be data sparsity and interpretability and computational cost because even if we reduce the dimensions, it still takes a lot of computational cost. So one of the optimizations can be done there. In future, we can try multi-model embeddings, that is, several models can combine together to create a certain embedding, or real-time adaptation can also be included in while computing those embeddings. That's all from my side. Thank you.
So I'll be carrying forward from this point onwards. Uh, I'll be talking about image vector embeddings and joint embeddings. Right. So the things that I'm going to cover are how image embeddings are actually generated, the mathematical basis of learning these embeddings, and the joint embeddings in multimodal settings uh, with architecture such as Clip and Dolly. Right. Okay, let's get started with CNN based embeddings. So CNN are essentially convolutional neural networks. What these are essentially are networks which can efficiently compute images and work with images for efficient vector matrices calculations, for efficient feature learning about different images that we have. What So let's talk about this their architectures, right? So convolutional neural networks have different kernels or filters, right? And we move them along in patches. So these are like odd dimensional features, odd dimensional filters. So for example, 3 cross 3 or 5 cross 5 or 7 cross 7 filters. Now we move them in patches on our image that we have. We basically convolute them, and we calculate the dot product of the filter and the specific image patch that it is on currently. Whatever value that we get is a singular value, and we store it in our output image or output activation map. Now, after we have moved this filter across the entire image and stored all these values, this constitutes one single convolutional operation, right? And we do this repeatedly over across many layers in order to get basically learn different kind of features that the original image has, so that the network can easily understand what are the different features, things like edges, corners, textures, fine textures in the image, the input image that we had given it to it, uh, given to the neural network as an input, right? Now let's talk about how exactly the mathematical basis behind this, right? Right. So the function that you are seeing here, Z, is actually the output of the entire network. The function can be treated as the network that we have learned, and the I, as you can see, is the input image that we have. It has the dimension h cross w cross c, h being the height of the image, w being the width, and c being the channel. By channel, what I mean is that, for example, an RGB image has three channels: red, green, and blue. Similarly, while computing an image through a neural network, something that we have seen on the previous slide, uh, the image gets downsampled or upsampled, and while downsampling, the height and width gets decreased, and we may want to increase its number of channels by increasing the number of filters that through which we are performing the convolution on the image, right? So basically, that is what channels are. Now we apply a convolutional operation on the image. As you can see, w times I is basically the convolutional operation. Now whatever output we get, we add a bias value which remains the same for the entire layer. The value, like the subscript values from I to L, are basically the layer positions, and W is the kernel, and like kernel values, which essentially are the weights in terms of our CNNs, which are updated as the loss function is optimized, and B is the bias value, which is also optimized. Now, whatever output we get, we pass it through a nonlinear activation. It can be a ReLU activation, or as simple as a sigmoid activation. Whatever output we get, that gives us an activation map for one particular convolutional layer. Now, we do this across many layers from 1 to L. Sorry. Whatever output we get now is an activation map. We pass it through, we basically flatten it out to get a linear, uh, like a linear array, and we pass, or a vector in our case, and we pass it through a linear layer to get basically the embeddings that we call as a d-dimensional embeddings. It can be like 2048 dimensional embeddings, or 1280 dimensional embeddings, or anything based on our neural network architecture. uh, let's take a look at one of these architectures. This specifically is the VGG19 model, uh, like 19 models architecture. So the input image is basically of height and width 224, along with three channels. Basically, it's an RGB image. Now we have gone through a series of downsampling operations, or convolutional operations, and we have increased the number of filters at each step in order to get more and more number of channels, so that it learns all the different kind of things which are encoded in the original input image. Now at the final step, we have passed it, we have flattened out the uh, like all the values that we had in terms of 7 cross 7 cross 512. If you multiply this value, what you get is 4096. So you have flattened it out, we have passed it through a linear layer, and we have got the final activations, like basically the final embeddings uh, for our model, for our input image, right? And if you pass it through a sigmoid layer, or sorry, if you pass it through a softmax layer, what we get are the class probabilities, which we do not need if you are just working for the embeddings, right? Vector embeddings. Now let's look at a vision transformer. So transformer architecture is something that was introduced in the space of NLP or text, but it has very nicely translated into images as well, and nowadays is being used in reinforcement learning and all these different paradigms as well. So transformer, what it does is that instead of working with a sequence as an auto-regressive network, it basically takes the entire input at once and processes it at the same time. Now, what enables it to do this is something known as positional embeddings, which I'll talk about in the next slide. But basically, to get sequence in for an image, what we do, like for text, it's very easy, because what you get as a sentence is already a sequence, right? It's a sequence of words which you transform into sequence of tokens. So for simplistic understanding, we can assume each word as a token, but that's not really the case. The tokens can be, even a blank can be like a spacebar can be constituted as a token, or just a singular letter can also be a token. It depends on the architecture that we're using. It depends on the tokenizing paradigm that we're using. However, for images, what we do is that we break the image down into patches. P cross P patches, which can be 4 cross 4, 8 cross 8, or 16 cross 16 patches, and we arrange them in a sequential manner. So basically, we flatten out these patches, and what we get is the sequence that we can now pass into the transformer as a single sequence, right? Right. So as you can see in the image, we had an original image. We broke it down into these 9 patches. We arranged them in a sequence, and we now passed it all at once to the transformer, along with the positional embedding. Right. Positional embeddings are now things which, instead of, like, in order to preserve the positional integrity of the sequences that we have passed, this positional embeddings comes into play, right? So these are basically a collection of sine and cosine functions that takes into account which position a particular sequence, a particular token in the sequence is at, and encodes that feature along with it, and that gets concatenated to the original embedding that we are going to learn through the training process. And these two things together concatenated basically gives the entire information that is needed for the model to work, right? The embedding layer is the one that is going to learn all the different semantic information about the original image that we have given to the transformer as an input, right? Now in this case, it is basically learning all these different features. As you can see, through after the mlp head, again, if in terms of a classification model, we can do something like a softmax operation to get the class probabilities, but in just to get the embedding, we can stop at the mlp head value, and like whatever dimensional vector that we have is the embedding in our case. And we can also get latent embeddings, like in terms of like what the value that we are concatenating with the positional embeddings are the latent embeddings for images and text alike. So let's now talk about joint embeddings. So in terms of shared modality architectures, for example, clip model or the diffusion models, we need to have something that can work with images and text at the same time, right? But these are very like two different modalities with very different representations. So to bring it to the same dimensional space, what we can do is that after getting the vector embeddings, we can transform it into the same dimensional space, or basically learn the embeddings in the same dimensional vector, and we can work with them now. And how to get the similarity between these two vectors are very easy. If we talk about like simplistic metrics such as cosine similarity, which is basically just the dot product of these two vectors divided by the like the product of their uh, modular values. So now what we get as an output is the cosine similarity, and if which is basically the cosine of the angle between these two vectors in the dimensional space that they are being projected in. So if their values are similar, they'll be like closer to each other, so their values would be closer to 1. And if they are not alike, they would be very different from each other. So if they're anti-parallel, the value would be -1. And if they are like not at all anything alike, something like an orthogonal vectors, then the value is going to be 0. Right. So let's talk about something which is the clip model, right? Clip is basically one of the most popular and one of the first models in terms of multimodal architectures. Now it has something known as a contrastive loss function. What this is, it basically contrastive in essence means something which introduces some kind of a contrast, right? So if things are similar, it goes the value is bumped up to 1. If things are dissimilar, the value is bumped down to 0, like in terms of loss function. This is what contrast means. So as you can see, as the like in, at the loss function that is given on the slide, we need to get this value closer to 1 if the similarity between the image and the text representation is high. So that minimizes the loss function, because the once the value inside the log function gets to 1, the value of the log function will be 0, which will minimize the loss function. And if the value is very different from each other, so if the text and image are nothing alike, then the value would be greater, the similarity would be closer to 0, which will give a log value of towards negative infinity, like limiting to negative infinity, which after getting multiplied with a -1, will bump up the loss function to a very high value, which is not desired, right? So we will learn a meaningful representation through this loss function while optimizing this loss function. Now on the right, what you can see is a joint embedding space. What happens is that the text encoder encodes the text into sorry, into a d-dimensional vector. Similarly, the image encoder also takes in different images and gets a d-dimensional vector again for these different images, and we take a dot product of these images with their corresponding text descriptions as well, right? So the values on the diagonal are meant to be high or should be high, and that is what we optimize while training, because the image and the text correspond with each other in terms of semantic similarities, and the rest of the values are trained accordingly in if to get semantic similarities and relations in terms of values, and in terms of some like values which can be understood by the neural network model and architecture to work with more tasks down the stream. Now, again, this diffusion model is something which also works with shared modalities between text and images. So, if we talk about like text to image generation, stable diffusion is one of the most popular models and one of the earlier models in this case. And what this does is that, as we have seen in the previous image, the clip embeddings, this that is what is computed for the text and the images, and the both are concatenated together and passed through the unit model to denoise the image. So essentially, initially we start with just random noise and sorry, and a description of what we want as an output. These two things are transformed into an embedding space and concatenated, passed through the unit model to, like, this is not exactly the original unit. It is transformed because it has like self attention and cross attention layers incorporated into it. And what it does is that it predicts what the amount of noise would have been added at a particular time step, and we basically remove that predicted noise, and whatever output we get is the denoised image, right? So basically the denoising happens over a certain number of time steps, 50 or 100, and whatever image that we get finally is the output image, which is completely denoised image, and that we that is what we work with. And the latent space that we have here is where the embeddings are basically stored, right? So while training of these diffusion models, the training happens through inspiration from an earlier model, which was the variational autoencoder. So basically it has a latent space wherein the embedding vectors of different images are, or different semantically images are closer in the dimensional space in which the latent space exists, right? So what how they do this is uh, through incorporating a decoder architecture as well. So after you have encoded the image into the latent space, the decoder basically brings together the different embeddings of semantically similar images closer to each other, and uh, basically removes or separates the embeddings of images which are far apart semantically, uh, far apart in the like the latent space as well. And that is how we get meaningful representations of these images in the latent space, which we can directly use instead of the original bulky matrices, three-dimensional or d-dimensional matrices, and like in terms of channels, and we can just have a linear vector which we can use efficiently for our downstream tasks. Right. So I'd like to conclude here by saying that embeddings power AI, and from search engines to image generation, these are very lightweight things which we can efficiently work with, and understanding that mathematics and architecture definitely helps us build better AI models. Thank you.